tease apart exactly why that is, but let's now just toss out a bit of jargon so that when we start seeing these things on the screen, it's not so scary. So I have to teach you how to count again. So we've done this a couple times now, right? You came in presumably knowing decimal, 0 through 9. We spent a little bit of time in week 0 on binary, where you only have 2 digits, 0 and 1. But we realized in the first week that if I want to express the number 0 in binary, it was actually pretty easy. I can just say 0. But then remember that we said, you don't typically just use 1 bit. You typically work in units of at least what? So at least 8. Right? A byte is 8 bits. So even though it's a little tedious to write on a chalkboard, really if you wanted to represent the number 0 in binary, you would probably store 8 bits, all of which are 0. And it got pretty easy after this. If you want to represent the number 1, you have 7 zeros and then 1, 1. But then we actually had to think for the first time, right, in this scenario where we can't just go 0, 0, 0, 0, 0, 0, 0, 2, because we don't have that digit. We only have a binary number of digits, 0 and 1. So we didn't do this. So what was the number 2 in binary? Yeah, so it was actually 1, 0. So we had to move this here. So it's like carrying the 1. This then becomes a 0. And if you then think back to what this is the 1s columns, the 2s, 4s, 8s, 16, 32, 64, 128, and so forth, if you have more bits. So even though it's a little longer, takes more chalk to write these numbers, we can represent all possible integers with which we're already familiar. So this is binary. We already know decimal. Let's introduce a bit of hexadecimal. Hexadecimal is going to be useful here only insofar as some of the numbers we're going to start seeing on the screen are a little less scary, although in reality we're rarely going to care about what the address of some variable is. It could be 1, 2, 3, 4, 5, could be 4, 5, 6, 7, it could be a huge number of digits. We just care that these addresses exist. We're not going to typically care what they actually are. But what we're going to start seeing in a moment is that a hexadecimal number, so that everyone can see, let me move to just the window up here. What we're going to see now is a whole lot of numbers that start with 0x, which is just a human convention that says here comes a hexadecimal number. Hexa in this case means 16. So in the hexadecimal system, you don't have 2, you don't have 10, you have 16 digits available to you. So how do you go about counting in hexadecimal? Typically, you would start at 0, then you would go up to 1. And thankfully, hexadecimal is actually a little easier. Now you can go to 2, then you can go to 3, then you can go to 4, 5, 6, 7, 8, 9, and ooh, very good. So it's A, it's not 10, right? So each of these digits, each of these values here can be any of 16 possible values. Of course, once you start counting at 0, you get all the way up to 7, 8, 9, and you want to say 10, but expressing 10 takes 2 digits, but we have 16 available. So the world decided that after you get to 9, you actually go to A, to B, to C, to D, to E, and capital or lowercase doesn't really matter. It's just a convention. And then after you get to F, which is actually the 16th digit, if we count all these up, I've just typed out 16 hexadecimal digits. What do you get to after F? 1, 0. So then you carry the 1. You go from the biggest value, which in the normal world is 9, then you carry the 1 and you get to 10. In the hexadecimal world, you get to F, then you carry the 1 and you get to 1, 0. And then it's 1, 1, 1, 2, 1, 3, 1, 4, 1, 1A, 1B, and you can keep counting up like this. So we're going to start seeing a lot of things in hexadecimal. What's nice about hexadecimal is that each of these digits, and there's 16 possible ones, takes up an exact number of bits. Every hexadecimal digit is 4 bits. So if you write 4 bits followed by 4 bits, you get a byte. So it's very convenient to express numbers as hexadecimal because with just 2 digits, you can represent a whole byte. Whereas in binary, my God, you have to write out 8 separate digits. So this is just a more succinct base system. Now we're going to see it in a very arcane sense this week and next, but fast forward toward term's end and we start doing things like web programming and a language called HTML and a language called CSS, cascading style sheets. We're actually going to see these things again because they're also used on the web for colors. So just to fast forward, if you ever want to express the color red on a web page, you can either just say quote unquote red, which is actually pretty compelling, or you can actually say FF 0, 0, 0, 0. And that should be consistent today, FF, but it doesn't matter. Now, why is this? Little teaser. If you've ever heard of the expression RGB, red, green, blue, the way we're going to implement colors in a few weeks, and also in the multimedia section of one of our problem sets, FF is kind of the biggest possible hexadecimal digit you can write. It's before you have to roll over to a 1 and a 0. Well, this means a lot of red, no green, no blue. So what's the result if you combine these various paint colors? Well, you get just red. So that's red. All right, so that was a bit of a tangent only to emphasize that we're going to start seeing these things now, but it's really not a big deal. It's just a more succinct way of representing numbers than binary is, and even than decimal itself is. So let's go ahead and solve something. I'm going to go ahead and open up a new window in gedit, and we're going to go ahead and try to compare something very simple. So let me go ahead and start from scratch here. The code is available online, and I'm going to go ahead and say, let's zoom in. Let's go ahead and save this as compare1.c. And I'm going to go ahead and say int main void. All right, and the goal of this program ultimately is to get 2 strings from the user and then just compare them and say yes or no, the user typed the same word twice, or he or she did not. So let's go ahead and say we want to get a string from the user. So printf. Let's just do something like say something. All right, I'll put a space for aesthetics. And now how do I get a string? A little recap. So string s, let's call it s1 because I'm going to need 2. So s1 gets string. OK, not quite. I need to now kind of remind myself, wait a minute. I've just used 2 functions that I did not invent. So what do I need to include at the top? OK, so CS50. And also, yep, standard IO for printf. And now it should compile OK at this point in the story. So let's assume that the user doesn't try to be difficult. He or she just types in a word. So now let's go ahead and do the same thing. And we could use, we could use a loop here, but it's only a finite number of things. So it's actually pretty reasonable just to copy paste these 2 lines of code and get something from the user, but this time say something again. So I want the user to type in some word, then another word. And now let's go ahead and compare these things. So we know how to do branches in both C and Scratch. So let's say if s1 equals s2. Well, let me go ahead and say to the user, printf, you typed the same thing, exclamation point, semicolon. Else, let's say printf, you typed different things, exclamation point, semicolon. Any bugs jump out at anyone? Or any syntax bugs, typos? OK, feels pretty reasonable, right? So we get a string s1, get a string s2. We then compare it. And I didn't make this mistake, right? This could be the first possible mistake. Very commonly happens. But I am using equals equals. And that says compare these things. Don't assign one to the other. So you print the type the same thing or different thing. So let's compile this. Let me go down to my terminal window here. Let me go ahead and do make compare 1. Looks like it compiled OK. Let me make this a little bigger. And let's go ahead and run compare 1, enter. Say something. Let's say hello. OK, hello. No, I didn't. Right? So let's try this again and make sure maybe we got it backwards. Right? So hello and goodbye. OK, so I'm half right. Right? So that's at least correct. And let's just do a sanity check. Hello. Hello. All right, so it feels like there's something going on here. So what might this be? Right? So there's clearly a lead-in today. It somehow relates to this stuff. But like, what really is probably going on underneath the hood that's breaking this program? Yeah?
Maybe you can compare strings in a picture or something?
Yeah, so I mean, that's kind of what it reduces to. Even if you're not quite sure at all on the why, feels like the only opportunity for the bug here really reduces to just one line. Every other line in this program is pretty straightforward and pretty uninteresting. So the decision point must be where the flaw is. And in fact, it is the case that you cannot compare 2 strings in this way. Why can we not compare 2 strings in this way? Because equals equals has worked for like 4 weeks. We've used it for chars and ints. It can break with floats and doubles, but that's a different issue. Remember, when you compare floats and doubles, because of imprecision, you might be comparing something that's ever so slightly off. But a string is a string. But what is a string really? What did we say, quote unquote, string is synonymous? Yeah, it's an array of characters. So really, remember, if we get rid of the CS50 library, we lose some of its synonyms that it's defined. And recall that we kind of peeled back this layer recently and then quickly hit it again. What string really is just a synonym for is char star. So star, we've just seen a moment ago, is apparently the solution to all of our problems, at least with regard to swapping things. But char, we've seen, it's just a character. So char star means pointer to character. Or if we boil it down to its basic definition, char star means the address of a character. So who cares? What is this really doing for us? Well, let me spin this around to a blank. OK, Sarah's coming with us. Let me spin this around to. All right. OK. So what really is char star? Char star is pointer to char, but that's just address of char. So what is a string? When you allocate s1 like this and then assign it a value, what's really going on? Well, on the left-hand side, what you're getting in RAM is, let's call it a square, a chunk of memory that is how many bytes? How many bits? In the appliance, at least, this is going to be 32 bits. The mere act of having written a star means you're going to get a pointer, whatever that is. And we can represent this pictorially with the square. And that square represents 32 bits. Now, we've drawn pictures like this before. If I've ever said int x on the screen with a semicolon, what that means is give me 32 bits and allow me to put a number in there. Well, that's all a pointer is. It's just a number. It just so happens that number has special meaning. It represents the address of something in memory. It doesn't represent an integer that I put in memory. So this is what S1 is. So logically, what is S2? S2 is just another such chunk of RAM, another 32 bits. So when I call getString, we already know, at least conceptually, that a string is an array of characters. And we know this, we've seen this, right? In PSET 2 with Caesar and Vigenère and the Hacker edition with Crack, you've actually traversed arrays of characters from bracket 0 all the way up to n-1. So what really is a string? What is getString giving you? Well, what getString does, and we'll see this week and next, is that when you type in the word hello as the human, getString is calling a special function, happens to be called malloc for memory allocation. And what it's doing is it's allocating a chunk of memory for you, and it's then putting in whatever letters you type. H, E, L, L, need a little more. O, need a little more, actually. What else is getString probably doing based on past promises? Yeah, it's putting that so-called null character, which we draw as \0. So what has getString been doing all of these weeks? It's been allocating with a new function called malloc, a chunk of RAM. But what's key about this chunk of memory is that it's back to back to back to back. It's not a little over here, a little over here, a little over here. It's all contiguous. And it's of size n+1 so that you can fit the string plus this null terminating character. So now, if a pointer I claim is just 32 bits. It's this small. This is clearly too small to fit HELLO \0. What's really going in here, do you think? Yeah, just the address of this, right? If this is memory, this is RAM, and RAM is like 2 gigabytes worth on your Mac or PC, well, we've claimed that you can say this is byte 0, this is byte 1, this is byte 2 billion, if you draw it as this rectangle as we keep doing. So these cells in memory, these chunks of bits, all have some address. This might be address 1, 2, 3, 4. This might be 1, 2, 3, 5, 1, 2, 3, 6, and so forth. What the numbers are doesn't matter, but that they have numbers does matter. So which of these numbers is probably going inside of this 32 bits? Which one do you need to know? It's really just the first. What's going to go in here is the number 1, 2, 3, 4 if 1, 2, 3, 4 is the physical address in memory of the first byte. Now, this is sufficient to remember S1, because if I know that the start of the string is at address 1, 2, 3, 4, how do I find the end of the string? Exactly. You just very simply, honestly, for loop, while loop, whatever your preference is, you start at that address and you check here. Is this the null character? 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 Is this? Aha, it is. That's the end of the string. So the function printf does something pretty much like that. It looks at every character back to back to back, just like you did with Caesar and Vigenère. And as soon as printf sees, wait a minute, this is not a printable character. This is \0. All 0 bits, it stops printing, it returns, and voila, you see some text, string of text on the screen. So now back to the flawed program. This s1 equals S2, what is it really doing then? If